All right, hello everyone. So today we are going to get through this one problem, and we are going to look at a bunch of different stuff as it relates to instantaneous centers of rotations and angular velocities and things like that. So the problem says block D moves with a speed of 3 meters per second. The question asks you to determine the angular velocities of links BD and AB. A helpful hint, if you haven't figured this out by now, usually, 95% of the time, questions will ask you to find things, and it's usually in order. If I tell you to solve A and then comma B, you should probably almost always solve A first, because it's probably better to do that. In terms of like solving A will solve B, but if you try to go the other way around, it might be 10 times harder. So that's usually for textbook problems. On a test, professors may know that and change the order, but at least for textbooks, it's usually a really good idea to solve things in order. So yeah, just a little hint there. But, so we are given this problem. We have a link AB, which is then attached to BD, and D itself is just a block that is moving 3 meters per second that way. I'm going to define the coordinate system here. So here's positive I, and here is positive J. So right-hand rule, that means positive K is this way. And we will be using K now because we're talking about rotations and angular velocity and stuff like that. So, point of the problem is to find the angular velocity of BD and to find the angular velocity of AB. So one note for my notation, when I say the angular velocity of link BD, it's also equal to the angular velocity of DB, because they're the same exact link. That doesn't matter, but just in case I rewrite it, so BD equals DB, AB equals BA. So if I write it a wrong way, it doesn't matter. I'm talking about the same exact thing. Okay, so to solve this, I am first going to start with base equations and then generalize it to this problem, and then I'm going to use my method that I always do of check marks and question marks. What do I know? What do I not know? So a good place to start, so angular velocity, so we're going to use this equation. Velocity of A equals velocity of B plus the velocity of A with respect to B. So this is just the base equation, right? I'm going to generalize, or ungeneralize this, I guess, rather, to our problem. So what I just said is usually it's listed in the order that you should solve, so BD. So I'm going to look at length BD right now. And I know something already about D. Velocity of D is equal to, we already have velocity of V, is equal to 3 meters per second in the I direction, but that is also equal to the velocity of B plus the velocity of D with respect to B. Any questions there? It's just this base equation. And the real important thing here is that I chose to analyze D because one, I know something about it given in the problem, and two, it's listed in this order, which, like I said, usually helpful. It's usually really helpful, the way that they list things, but sometimes it's not. Regardless. So taking this equation, velocity of d is equal to the velocity of b. I'm going to take this velocity of d with respect to b term, and I'm going to substitute something else. I'm going to use the velocity, or the angular velocity, dB, crossed with. So VB stayed the same, VD stayed the same. I substituted the velocity of D with respect to B with the angular velocity cross the distance from D with respect to B. Does this make sense here? We all know this equation. When you have like relative velocities, the base equation here is, velocity A with respect to B is equal to the angular velocity of like the system AB, then crossed with the point, the distance from A to B. But you should see that this is the cross product. So when I'm saying distance, it's actually, that's not the correct term for it. We need to keep the unit vectors in mind for how we're going to do this. So I'm also going to give a little more intuition on this equation right here, because when I first saw this equation talking about how in the world does the velocity, relative velocity, equal the angular velocity multiplied by just some distance term. So if I have this marker right here, and it's going to, when it rotates like this, it's rotating about my finger right now, like where I'm holding it. So if we think about the tip of it versus like maybe where this black line starts, if I look at it, the velocities must be different if we're looking in the same time span. So maybe the angular velocity of the entire system itself is the same when I'm doing this. This right here is the term that changes, the distance. So again, I have the velocity at the end of this, and somehow that velocity is faster than the velocity towards my finger. And that's because the angular velocity of this marker when I do this is constant, but this term is not constant. So that's why, that's a little bit of where this equation comes from. So, okay. So we have the velocity of D. We do not have the velocity of B. I can find this term, so I'm going to put, what should I put for that? I'll put like a check mark, but with an X, meaning we still have to do some work for it, but we can find it. And then the angular velocity of dB, I don't have a colored marker, so usually I would have done this one in like red, and I would have done this one in green. This is the whole point of the problem, is finding the angular velocity of dB, so that's okay not to know. But anyways, looking at this, we can't solve this because even though I can get this term, and I'm going to eventually, it's going to take some work, and I also don't have this, so that's a big problem right there. Okay, so you might, what you might be thinking now is, okay, we can't find anything else more about the link B to D. So let's look at the link A to B, and then since it's a connected system, maybe we can find something from A to B and then relate that to link BD. So in the same fashion, I am going to say the velocity of B is equal to the velocity of A plus the velocity of B with respect to A. Same exact thing I did here, just I'm looking at a different part of the system. So there is something special about link AB. A is fixed. A is not going to move. So velocity of A is 0. Velocity of B is just equal to the velocity of B with respect to A. Then, doing exactly what I did up here in this equation, that is equal to the angular velocity of link AB crossed with the, I think the right term for it is position vector. The position vector of B with respect to A. Okay. So, at this point, both of the variables that we're solving for have shown up in the equations that I've derived. So this is usually a good sign that you're on the right track, because with the base equations that I had, like starting from here to go to here, the variables that I'm trying to solve for weren't in the equations. So you had to use your intuition to see how does what the question is asking me relate to what I can readily apply. So at this point, we're trying to solve angular velocity of BD, and we have that. It showed up right here in this equation. And then when I looked at BA, the other term showed up, the angular velocity of AB. So, looking at this thing right here, I can solve for this. I don't have it yet, and I'm going to eventually, but I don't have it. This is the whole point of the problem, so it's okay not to know. But you still do not have the velocity of B. So we have two equations and more than two unknowns, so we need to do something else. So this is where you need to know that I've run out of everything I can do. I need to somehow apply some other method, because I've derived all that I can just looking at this and applying the base equations. So I need to apply something else to derive more equations. That comes up all the time in dynamics. You come up with these equations, and then you find out you have more unknowns than equations, and you need to apply more methods to get more equations. So, instantaneous center of rotation. So I'm going to redraw this diagram, but with the velocity vectors more pronounced. So there's our system. Velocity of A is fixed, 0, there's nothing. So here's the velocity of D vector. I, J, and K. This is the velocity of D, and it's 3 meters per second. And we're given that it's only in the I direction. So, velocity of B. In the problem, you're given that this angle is a right angle between these links. And when this moves, when D moves, so is link A and B and D is going to move. So what I can say there is that the velocity of B is then along this line when D moves. So to kind of illustrate that, it's like if I have okay. So this is our system, right? And it's fixed right here. But if this part is not fixed and this moves, it's going to go like that. This is what we're looking at right here. So my hand is point D. When it moves this way, the whole system is going to go like that. So that's what you're looking at here. Okay. So this is really good because we're applying instantaneous center of rotation, and we see that these velocity vectors, they definitely intersect. The perpendicular aspect of them intersects, and that's how we derive more equations. So draw a line perpendicular to this, to the B vector, and then a line perpendicular to the D vector. Right here is the instantaneous center of rotation. I call it the ICR. So we can now use this triangle that's formed here. I'm going to draw a line right here. So we have a triangle that's formed there, and now we can derive more equations. So that is how we are going to solve the problems over there. So reiterate one more time. We applied base equations, made them specific to our problem. We saw all the variables that we needed to solve the problem, but we found that we had more unknowns than equations. So I then applied the instantaneous center of rotation, and I just found that there is an instantaneous center of rotation. So now we're going to use this triangle and the angular velocities and velocities associated with it to find out the unknowns in those equations. Then once we do that, we're going to stick it back into those equations and solve. So I'm going to draw this triangle right here, which is very special for our problem. So all you're looking at, point B is right here, point D is right here, but now we're looking at a triangle with the instantaneous center of rotation. In the problem, the length BD is given as 0.4 meters, so we have that. We know this angle right here is 45 degrees from the problem. This angle is the exact same thing as this one right here. That angle is that angle. And then from that, this one also must be 45 degrees because this relative to that is 90 degrees. So we're starting to find out things about this triangle, which is very good. So you then know that this is 90 degrees because this line right here, this one that I'm pointing to, is this perpendicular line. By definition, perpendicular 90 degrees. So looking at this triangle, I know two angles and I know a side length. I can solve this entire triangle. And why would we even want to do that? Well, this right here is the position vector B with respect to the instantaneous center of rotation, this side of the triangle, and the hypotenuse over here. This is the position vector of D with respect to the instantaneous center of rotation. So I think everyone would agree with me that we have two angles, and this side length right here we know. So we can find all of these, everything right here. But why would you even want to do that in the first place? Well, the velocity of D is equal to the angular velocity of D crossed with the So the velocity of D is equal to the velocity of the instantaneous center of rotation plus the angular velocity of link BD crossed with the position vector between the 2 points. By definition, this is 0. The velocity of the instantaneous center of rotation is always 0. Looking at this, the instantaneous center of rotation is my finger. It's always 0. It's rotating about that. The velocity of the instantaneous center of rotation is always 0. So now the problem gives you velocity of D. This is 0. I'm trying to solve this right here, so that's okay to be unknown. And I don't have this yet, but I can find it. And that is why I'm solving this triangle in the first place, right? So now we're going to use trig to find this. And then once we have that, it's just computing, and then we've solved half the problem. So let's do that. Let's solve this term right here. So this is just from the Pythagorean theorem. So I'm applying tangent to solve this first, and then I'm just doing the fact that a squared plus b squared is c squared. So it might look like I'm going a little bit out of order, and I am, but it doesn't really matter that much. We're going to need both these terms anyway. So right here, tangent of 45, tangent of this angle is equal to this term divided by this term. Right? Tangent of this is this divided by this. So I can directly get this side length right here. It turns out tangent of 45 is a 1, I believe. Yeah, it's 1. So RB with respect to the instantaneous center of rotation is just 0.4. So this is 0.4 meters, this is 0.4 meters, which we just found. So this is what I meant, a squared plus b squared. So to find this term right here, all it is square root 0.4 squared plus 0.4 squared. So then position vector of D with respect to the ICR is now this 0.4 squared plus 0.4 squared, and then the square root of that is 0.5656 meters. Is there any questions so far? Okay. So I can now get rid of this thing. Looking at this equation, velocity of d is equal to angular velocity of BD, then cross product with the position vector that I just found. So one equation, one unknown, half the problem's done after I compute this. So doing that. Just in case you forgot the cross product and things like that, velocity of d given as 3 meters per second in the I direction. That equation right here becomes 3 meters per second in the I direction equals angular velocity of BD. And I'm going to assume that the angular velocity of link BD is in the positive k direction. Even if your intuition is telling you that's wrong, it's always a good idea to assume positive. Because if your answer comes out negative, you just know that your assumption was wrong in the end. But if you assume negative, it's like the idea of like double negatives. Like this is not incorrect when you should have said this is just correct, right? So usually it's, at least for me, I always assume positive directions because it's way easier to tell what your answer means. So angular velocity of link BD is equal to 3 meters, the velocity of D, 3 meters per second is equal to the angular velocity of that link, then the cross product with this term right here. That's what that equation simplified to. So 3 meters per second, the I direction, equal to crossed with. So at the beginning when I mentioned this was a distance, it's not really a distance, it's a position vector, meaning this term right here has direction. So I'm saying d with respect to the instantaneous center of rotation. So although the magnitude of it is 0.5656 meters, it has a direction to it. So d with respect to the ICR, how I like to remember it is so when I hear A with respect to B, 2A from B. Any questions there? Because these directions are important. So 2D from the ICR. I'm starting at the ICR, I must have went down. So this right here becomes negative. Negative 0.5656 in the J. Equivalent would also just be saying positive, but in the negative J direction. Doesn't matter though. Either way you do it, somehow this term is becoming negative. Cross product. Okay. So a helpful tool to evaluate the cross product is everyone cool if I erase this part? If you had a Rico, she probably taught you this tool. And it's really good, so years later I still use it. Okay. So you put the unit vectors just in a line like this, so I, J, K. And for instance, what I'm doing right now is K crossed with J. So that's K crossed with J. And since I'm going opposite to this, this line that I drew, it's going to be negative. For instance, another example, if I go K crossed with I, it's going to be positive J because I'm following this schematic that I drew. Any questions there? No? Okay, K crossed with J. K crossed with J equals negative I. So I still have this negative term. It's just pure multiplication, 0.5656 times the angular velocity. And this was negative, so that showed up. But the result of the cross product was negative I. So this is going to be 3 meters per second equals 0.5656 times the angular velocity of link BD. So what I'm about to tell you is probably the most important part for knowing that you're correct and what you've done up until this stage is right. And this is really, really important for like taking a test. When I did the cross product here and looking on this side, I only had components in the I direction. If when I do this cross product, my component tells me it's not in the I direction, you're wrong. You need to restart. This is saying something in the I direction equals something in the I direction. And yeah, that is true. That can be true. But if I did this cross product and my final unit vector was in the K direction, I can never equal K. So this is really important right here. 3 meters per second in the I direction. When I did the cross product, I got something that was also in the I direction. So if you're at a point on a test or during a problem and you get, 5 in the I equals, 3 in the K crossed with 2 in the I, you're wrong, because this will lead to J. K cross I is going to be J of some sort. So, yeah, always check that. That's how you can verify if you're going in the right direction, at least. Okay. So, have this one equation, one unknown. Angular velocity of link BD is now just 3 meters per second divided by 0.5656. And that is 5.3 radians per second. And that is positive K. So that's half the problem. We solved half of it. Any questions? Okay. Everyone good if I erase like that part? Yeah. Okay. So, yeah, what's up?
Can you explain how it was negative 0.5656 and a negative I?
Yep. So, are you with me right here?
Yeah.
So K cross J, this little tool right here, if you go against this line, it's negative.
Okay.
So for instance, if like this K crossed with J is equal to I,
Okay.
I'm going in this direction. K cross J is equal to negative I though. K cross J. So it matters what direction you go.
Okay.
So I had a negative here to start, and k crossed with j. K cross j is negative I, so that's where this negative I shows up. But I also, the term itself, the number was negative, so it cancels out.
Okay, thank you.
Yep. All right, so we know the angular velocity of this link now. We can find the angular velocity of link AB. So, solving this, starting again. Velocity of D is equal to velocity of B plus the velocity of D with respect to B. We have velocity of D. I'm going to decompose that once again. Okay, so the 3 meters per second in the I direction is showing up again. Velocity of B we don't know. I just found angular velocity of link BD, and I can get this term right here. So, obviously have that. So this is one of the base equations that I started with, and now we can, we're almost there to solving it. So, the only thing we don't know here, the only thing we have left to do in this equation is position vector 2D from B. 2D from B. Position vector is pointing this way. 2D from B. So that means RD with respect to B is equal to everyone good if I erase this? Yeah. Minus 0.4 sine of 45 in the J. If we're thinking 2B, we have to go positive in the I, then negative in the J. So that makes sense. All right, cross product. Because we're getting the velocity of B. Actually, first. You might ask, why would you want the velocity of B? I realized I erased it because I, ran out of space, but so the velocity of B is equal to the velocity of A, 0, plus the angular velocity AB crossed with R. So this is the other base equation I started with, right? I'm solving velocity of B right now. And link BD allows me to solve this. What I'm going to get from this computation that I'm about to do, I can then solve the base equation that I started with in the beginning. So that's the motivation for why I'm even doing this one in the first place. So that becomes 3 meters per second. 0.4 times cosine of 45 and 0.4 times sine of 45 is both about 1.5. So No, it's not. Okay. So at this point, it's just cross product and then solve, but I will do it now. Drawing this thing again, K crossed with I, K crossed with I, positive J. So, and then 5.3 times this term right here is the 1.5 that I mentioned. 1.5, and that is positive J. Same thing, 5.3 in the K times negative 0.4 times sine of 45 in the J. We have K cross J, negative I. And it's 1.5 again. So, (3 meters per second in the I direction equals the velocity of B plus 1.5 in the J minus 1.5 in the negative I, so that becomes positive I. Okay, so we can solve for the velocity of B. Velocity of B is 1.5 in the I minus 1.
Shouldn't it be negative 1.5 J?
Yeah.
And then just take the square root of those two and square them. Or the, what's it called? Put
The
in the square
magnitude.
root and then.
Yeah. I know the answer is 1.5 in the I plus 1.5 in the J, so I missed a sign somewhere. But it's really not that important. I missed a sign somewhere, and I'm not going to go and find it. But the ideas and the concepts are right. This is the velocity of B. And yeah, like he said, if you want, I always keep it in terms of I and J, but if you want to find, you can do 1.5 squared plus 1.5 squared, square root of that, and then you could also find the angle of it. I'm not going to do it because I think it doesn't, if the problem asks for it, you need to do it, but I don't think it, I personally understand this more. So, there we go, we have the velocity of B. Last step. Finally, last step.
Wait, how do we get rid of the 3 meters per second?
Oh, yeah, so solving this equation, minus 1.5, 3 minus 1.5 is 1.5.
Oh, okay.
And then minus, this somehow needed to be a minus actually.
Okay.
That's what, so this would end up being plus, but yeah, that's how I got here.
Okay.
Right, so, right, we are almost done. Can I erase this? Last step. Now that I know the velocity of B, I'm using this equation now. The equation we started with. Angular velocity AB crossed with are b with respect to a. I have this from right over there. Angular velocity of AB is the entire point of the problem. The position vector from B with respect to A, I don't have it yet, but I can get it. It's super easy to get. And I'm not going to derive it for a third time just because there's literally only 3 minutes. I'm just going to tell you what it is. So this is the angular velocity of AB in the K crossed with, what does it end up being? 0.4 cosine 45 in the I direction plus 0.4 sine 45 in the J direction. So you have that. This again is now what, 1.5 in the I plus 1.5 in the J equal to this cross product. So doing this, you get so I've ran out of time, but this is really just calculation at this point. So I've done the cross product. So we have K crossed with I and K crossed with J. And one really last thing, we saw that the velocity of B had components in the I and J direction. So it's a really good sign that when I did this cross product, we had I and J components again. So last step, literally last step, solving this, looking at just the I components, for example. So 1.5 in the I is equal to negative 0.282 angular velocity of AB in the I direction. Just algebra at that point. Velocity of AB is negative 5.3 in the K direction. That's the answer. And one final thing to say about this. The original system that we were looking at, links, we have link AB on this side, link BD on this side. We found that link BD was rotating this way, rotating counterclockwise. So it makes perfect sense that link AB is going to have the exact same speed, but just in the opposite direction of rotation. So that's where your engineering sense needs to come into play. If we got, at the end, this was positive K, and the other link was also positive K, that doesn't make any sense. Because if I have two links like this one rotates, and they're connected where my finger is meeting this, the other one has to rotate in the opposite direction. If this rotates like this isn't going to go with it. So, at least in this system. So, it makes perfect sense that we have exactly the same magnitude, just opposite direction. So that's it. That was a hard one to get through, but I hope you guys understood the process. It's obviously a lot. I mean, you know, I could have done 3 problems, but I think getting through one and looking at every single step is better. I hope so, at least. So, all right. Thanks, guys.